Hello class, so today we're going to pick up on correlation and regression. It's our last week of statistical quantitative analysis. Okay, so in review, remember there's two kinds of social scientific tests. You have the test of differences, so remember the ANOVA, chi-square, all of those. And then you have tests of relationships. So tests of differences are all about what are the chances that when I compare these two different groups, that their differences are going to be more than beyond chance. Tests of relationships are all about how are two different variables, what's the likelihood of their correspondence being significant, okay? And that's where correlation and regression come into play. So it's very possible for a scientific experiment to do both of these. So don't feel like you're always choosing between one or the other. It's possible to compare differences between two groups and then ask what's the correlation between some of the attributes of some of these two groups and their effects or their dependent variables. So definitely possible to do both at the same time. But for correlation today, correlation is simply the measurement of how the variation of two variables correspond with each other. So what correlation is all about is basically correlation likes to work on scattergrams, so they're like these little dots, that kind of thing. And what correlation is basically asking, if this was a variable and that was a variable, so maybe it's like happiness and GPA. So maybe happiness is down here and GPA is up here. Correlation is all about to what degree when one goes up does the other go up, or to what degree that when this changes, like when happiness changes, GPA changes. Okay, so maybe here it starts to change and then here it starts to change. So what degree of correspondence is there between these two variables as they change? Okay, so that's all correlation is basically measuring. It's not measuring to what degree does GPA cause happiness. It's not asking that. And it's not asking does happiness cause GPA. It's just saying to what degree do GPA and happiness correspond with each other. So as one changes, how does the other change alongside with it? Okay, so the key word with correlation is correspondence. Okay, and that will avoid some problems and misinterpretations down the road. So when you're reading correlation studies, there's a couple of different coefficients that you need to understand. One of the most common ones that you'll see is the Pearson Product-Moment Correlation coefficient. I know they have to make it some really long name, so a lot of people just call it the Pearson coefficient, but if you just want the long formal name, you can write all of that down. And it's signified by R. So R is basically measures the correlation or the correspondence between two variables that are both interval or ratio data. So something to keep in mind, the Pearson correlation, or R, is only applicable when both of your data, your x and your y, are interval and ratio. So if you still don't understand what interval and ratio data is, Rainey sent out a video about that, and so make sure you understand those things, because it makes a huge difference which analysis you use depending on what kind of data you're collecting. So the Pearson product moment will measure that correspondence between those two kinds of variables. So example might be the amount of time studying for an exam and the score on the exam, right? So amount of time is interval and the score is interval. So there you see you can do a correlation between studying and exam scores, okay? So that's the Pearson product moment correlation. So there's some things about it that we need to understand. First off, this correlation coefficient measures two things. First, it measures the direction. So correlations can either be positive or negative. Okay, so if we were to draw a positive correlation, okay, then actually I think I actually have that coming up. Right here. So correlations can go different directions. So in a positive correlation situation, when one goes up, the other goes up. Okay, so this would be an example of a positive correlation. Because as you can see, as we move along the x-axis and we move up the y-axis, the variables get bigger, right? So as this is going up, that's going up as well. So that's a positive correlation. So they're both moving up at the same time. A negative correlation is where, so if you wanted to like put it this way, as x goes up, y goes up, okay? So that's a positive correlation. With a negative correlation, it's the opposite. As x goes down, y goes up, okay? So here, or in this case, x is actually increasing, y is decreasing as x is increasing, okay? So as we go along the x-axis, the y is going that way, okay? So as we increase, y is going down, okay? So it can be the converse, so what you would do is you could do x increase, y decrease, or you can do as x decreases, y increases. So either way, it's going to be a negative correlation. The fact is, both are not corresponding with each other. And so technically, too, you could have as x goes down, y goes down. That would technically be positive as well, because it's going in the same direction is the idea. Here, in this example, you have no correlation, okay? And we'll talk about that in a second. So the Pearson product moment will tell you what direction a correlation is going, okay? So it's either going to be positive, so both are going up or both are going down, or it's going to be negative, they're inverse. So sometimes it's called, a positive correlation is often sometimes called a direct correlation, and a negative correlation is sometimes called an inverse correlation. So it's all different words to say the same thing, okay? Then you have the strength and magnitude. So when you look at an R, or a Pearson Product-Moment Correlation coefficient, it's going to be on a scale of -1 to +1, okay? So it's going to be -1 to +1. So in a zero correlation standpoint, like here, R would be 0, right? There's no real correspondence. As x goes up, y goes up. You don't really see any kind of trend, right? So R would be 0 here because there's no correlation. In a perfect correlation where R is 1, okay, you would literally have a straight line, okay? There, R would be 1 because basically it's like a 1-to-1 correspondence between x and y, okay? But what ends up happening is we don't get this necessarily, but we don't get this either. We usually get something that's like, you know, a little bit more dispersed. So you get like an R of like 0.25 or an R of like 0.35. And so it's trying to give an overall measure of how closely the variables respond. So the limitation, and we're going to talk about this later, to R is that it's hard to imagine what an R of 0.25 looks like versus like an R of 0.45. So that can make the Pearson Product-Moment Correlation coefficient a little bit less useful because it is hard to conceptualize what does a 0.25 correlation look like in terms of like a scattergram or something like that. It's just hard to envision. So there's other measures that we use for correlation or other coefficients that we use. A very popular one is the coefficient of determination, or R squared, or lowercase r squared. And this tells us how much of the variance in one variable can be understood or explained by the other variable in terms of a percentage. So the coefficient of determination is kind of like an effect size. So your R might be something like 0.25. Your coefficient determination is just going to be 0.25 squared because it's just basically R squared. And that will give you a percentage of how much the variable of x explains the variance in the variable y. So here's an example of how it might look. So let me erase this. The correlation between GPA and ACT scores was positive, and so this is from a study. Moderately strong and statistically significant. So here you see the R, and so that's the Pearson Product-Moment Correlation. You see it's 0.43. So between 0 and 1, you know, it's pretty moderate, right? And they even said that moderately strong. Now, in a correlation situation, you're going to still run a test of statistical significance to make sure that the correlation coefficient that you got wasn't just by chance. And so that's where the p-value comes back. So if you don't remember what a p-value was, see last week's lecture. But we can see that it's a 1 in 1,000 chance that you got that score. So that's the correlation. Then it says, the coefficient of determination, r squared 0.18, revealed that 18% of the variance in ACT test scores was explained by students' GPA. So in other words, ACT test scores has an 18% correspondence with students' GPA. So as your test scores go up by a certain percentage, your GPA goes up by a certain percentage, okay? Or at least that's the correspondence between the two. 18% of the variance in the ACT test scores is explained by the student's GPA. So that's the coefficient of determination. So that's a bit easier to understand than the R of 0.43. We can understand this because we say, oh, okay, 18%. We get it. So another way to think of coefficient of determination, think of it as an effect size from last week, but just for correlation. I think that's a pretty safe thing to say. So that's another way to look at coefficient of determination. Now, there's a couple of things about correlations. There's two important things to note about them. The first thing is that correlations assume linearity. And so correlations, let's see here, okay, can only deal with situations where there's some kind of linearity involved. A situation where a simple correlation would not be helpful are in situations that we call curvilinear relationships, okay, where the line might look like this. What are some cases of curvilinear relationships? Here's one. How about we say medicine, the role of, how about number of drugs taken? So like medicine, we'll measure it by number of drugs. And reported well-being, okay? I'm gonna use a different color. So let's say like, 1, 2, 3, 4, 5, and well-being's on a scale, 1, 2, 3, 4, 5. 5 being really good, and happy. One's like, I'm dying, I need some morphine or something. Okay, so here's where a curvilinear relationship might exist. So you're sick, right? And so like, you need to start taking medicine. So maybe on day 1 of medicine, you're still feeling kind of bad. But as you take more medicine over time, you start to feel good, right? Well-being's going up. But if you keep taking your medicine, now you're starting to OD on NyQuil, right? So you start ODing on NyQuil, that starts catching up with you, and then eventually you start feeling really bad again. And then you have an addiction, and then you have other problems, and then well-being goes back down. So that would be a curvilinear relationship. It starts off and it goes up, but then at some point it goes back down, you see? So that's curvilinear. You can't really do a correlation on this because it's not like this. You see what I mean? Like it goes up and it goes down. So correlations are not equipped to handle these kinds of situations. You have to use other kinds of tests, which we're not going to talk about in this class. The other is that correlation does not mean causation. Now, you can all kind of understand this. I'm sure you've heard this a jillion times in science classes and, memes on Facebook and all that stuff. But here's the thing. Correlation does not mean causation. However, correlation is a necessary ingredient to establish causation. So here are the 4 things you have to do to establish causation scientifically. The first thing is the predictor variable has to precede the dependent variable in time. So remember, you have the independent variable, which is the variable you're playing with, and the dependent variable, which is the result, the outcome of playing with the independent variable. So the predictor variable has to be there before the dependent variable ever comes into play. So for example, let's say we were wondering, does inflation cause unemployment? Okay, so what you have to prove is that in a period before unemployment sets in, inflation goes up. And then once inflation goes up, then unemployment starts to go up. But if it's the case that unemployment goes up and inflation goes up at the same time, like they're going on at the same time, then you're not proving causation, you're only proving correspondence. You're only proving a correlation. So what you have to be able to prove, or you have to be able to show, that we can have high unemployment. We can only have high unemployment unless we have inflation first. You see what I mean? You have to prove that inflation has to come first before you can have high unemployment. Okay, the second thing, the two variables have to be correlated. So that's where your correlation study comes in. You have to show that whatever relationship exists between the two variables, it's not just by chance, and that it's strong, right? And it's not just some kind of weak thing that you might have just gotten by pure luck. Then you have to rule out extraneous variables. So what you also have to rule out is, sure, maybe the independent variable can precede the dependent variable, but you still have to wonder, like, is there a third cause? So maybe with the inflation and unemployment, sure, maybe inflation starts to go up, then unemployment starts to sit in, but maybe it's not because of inflation per se, it's because of fear of the crash of the stock market, like insider trading or something. So you have to be able to rule out all the additional causes that could be explaining why these changes occur. And then lastly, there has to be a causal mechanism of explanation. So what you have to be able to show is not just that there is a relationship, but there is a particular cause or mechanism by which the relationship occurs. So let's say that we've done the first three things with inflation and unemployment, and we've shown that inflation precedes it. There is a correlation between inflation and unemployment, and we've ruled out all other extraneous variables. So the next question is, well, so we have this relationship now. So how does inflation increase unemployment exactly? What's the causal mechanism? So you might have to then figure out, well, what's that mechanism? Well, maybe it's that when inflation goes up, the value of money goes down, employers can't pay their employees, so they have to start letting them go because they can't afford them anymore. So the causal mechanism would be the dollar causing employers to not be able to hire employees anymore. You see, so there's a mechanism there that you can pin it to. It's not just kind of a random, I don't know, for some reason they just do. You have to have, here's the mechanism by which this occurs in the world. So those are the four criteria for establishing causation scientifically. So you want to make sure you know these so you don't make mistakes about attributing causes to things that are not really causes. So there are other correlation coefficients for different situations. So you use the Pearson Product-Moment Correlation Coefficient when you're dealing with interval ratio and interval ratio variables. So if your x is interval ratio, that's an x, and if your y is an interval ratio, okay? So that's the only time you can use a Pearson. There's another called a point biserial correlation coefficient, and that's when you have an interval ratio and a dichotomous nominal variable. And so for those of you who don't know what dichotomous means, it means only two choices, a dichotomy. So an example might be like, gender and type test scores. So gender is a dichotomous nominal variable, in most places. So male or female, and then, test score, ACT score, something like that. So that's an interval, that's dichotomous. So there you would use a point biserial, and it's a nominal variable. So it's a dichotomous nominal variable. You can do voter, non-voter, PC owner, Mac owner, and then some interval ratio. That's point biserial. That's when you'd use that instead. Then there's the Spearman rank order coefficient, and that's when you have two ordinal variables. So remember, ordinals are rankings of some kind. So in that case, you would use the Spearman rank order coefficient. And then you have the phi coefficient, okay? And this is when you have two dichotomous nominal variables paired up against each other. So like you might do like a male, female, Sanders and Clinton. Now you might think about last week, well, couldn't you just run a chi-square analysis? Yeah. So it just depends what you're interested in and what you're trying to figure out. If you're trying to figure out a correlation or if you're just trying to figure out test of differences. So, very possible you could do a chi-square as well. It just depends on what your purposes are. All right. So that's basically correlation. Pretty easy, I think. Now we're going to get into regression. So here's the deal with here's some limitations to correlation. So correlation doesn't distinguish between independent and dependent variables. So when you're doing a correlation, you don't really care which is the x. Like you don't care like what's the independent variable and what's the outcome variable. You're just putting two variables together and wondering if there's any kind of correspondence. Because remember, correlation is correspondence. The other issue is that correlations only produce coefficients. So remember, we have like the r equals 0.12 or whatever, and it's hard to imagine like, well, what does a 0.12 correspondence look like? So then you have to use the coefficient of determination, which helps, but it's just kind of like you just get a coefficient in the end. That's all correlation gives you. So there's this other thing that rides on correlation, but it's just a little bit different, and it's called regression analysis. And they're usually married together because regression is basically just a bit more advanced form of correlation. So there's different kinds of regression analysis, and what regression analysis does, it allows you to look at a predictor variable and a dependent variable. And in simple linear regression, you're going to measure the correlation between one predictor variable and one dependent variable. So yes, there is overlap between simple linear regression and correlation, because basically it's the same idea, just now you're recognizing a correlation as a predictor variable and a dependent variable. So don't worry about what's the difference between simple linear regression and correlation, because they're basically, for all practical purposes, the same. We use regression analysis when we want to do multiple regression. So what if you want to measure two or more predictor variables on a single dependent variable? So let's say I want to study like how does height, exercise, and calories predict weight. Okay, if I just did height and weight, I could do a correlation for that. But if I wanted to do height, exercise, and calories intake, and then try to measure weight, what you want to do is a multiple regression analysis. So basically, multiple regression analysis is kind of like correlation, but still a little bit different, because what multiple regression analysis provides, and what regression analysis provides in general, correlation provides a coefficient, right? So we'll put correlation equals coefficient. Regression produces an equation, okay, and like an equation line. And naked statistics will talk about this too if you haven't read it yet. So multiple regression then, two or more predictor variables on a single dependent variable. Now here's what the measurements include. A multiple regression will tell you whether your variables as a group correlate with the dependent variable. So if I was doing, height, weight, and calories, I can figure out if that predicts weight. Okay? I can see, does all three of these variables as a whole predict that or correlate with that? I can also see whether each of the variables as individuals correlate with the dependent variable while controlling for the others. So what I could also do with multiple regression is I could say, okay, how does height specifically? So I could break this up and I can say, how does height predict weight? How does, wait, I meant to put something else. I meant to use a different variable. Height, exercise, and calories. So how does height predict weight? How does exercise predict weight? And how does calories predict weight? Okay, yeah, sorry about that. I'm like thinking of all these things. Okay, so height, exercise, and calories. How does height predict weight? How does exercise predict weight? And how does calories predict weight? You see, so I can break it up into individuals as well to see how they work. So I can look at how they work as a group, or I can look at how they work as individuals. Thirdly, I can also figure out, as a result of being able to break up the variables while controlling for each other, which one is the strongest predictor of the dependent variable. So what I can do is I can look at height. I know it's kind of messy now because I've written on it several times. So let me just do that. Let me clean that up real quick. So I can look at height, and then exercise and calories. I can look at height and I can hold these constant and see how much does it predict weight. And then I can hold height constant, look at exercise, see how much it predicts weight. And then I can hold height and exercise constant, look at calories and see how much it predicts weight, and then I can figure out which one has the greater percentage of predictive power in terms of weight. So regression analysis then just makes it easier for us to look at more complex situations. Instead of just looking at one variable on one variable, we can look at multiple variables on one outcome. Okay, so that's that. So the next part is we have to learn regression coefficients. So like I said, regressions produce lines, whereas correlations produce just regular coefficients. So a regression equation is y equals a plus bx. And so y would be like the predicted outcome, a is the intercept, b is the slope, and x is a particular moment or data point. So this should make you think of from like high school. Remember from like high school algebra, y equals mx plus b. This is basically that, but just for statistics, okay? And remember, m is the slope, right? So like you have like a line, and m is like the slope, you know, up and then down, right? If you remember all that from algebra, because like remember you had like the quadrant, you had like the positive quadrant and the negative quadrant and all that. And so y is like the slope, and then b is like the y-intercept, right? So if any of that rings a bell. But basically, that's what regression kind of is. That's what it's operating off of, okay? So think of a as like the starting, like intercept. Think of b as the slope of the line, and then x a particular input of data. Now, this is for a simple linear regression, if we just had two variables. But remember, for the most part, you use regression when you have multiple variables. So a multiple variable regression, or they'll call it multivariate regression, might look like this. Y equals a plus bx1 plus bx2 plus bx3. It can go on forever. You can keep adding variables. So each of these is a variable. Like this could be, so y could be weight, and then a is an intercept, and then b is like the exercise, calories, and height, right? And so each of these is going to have its own slope and its own data input, okay? So this would be a regression equation. So what you need to know in terms of understanding regression coefficients when you read these kinds of statistics. The b is an unstandardized regression coefficient, or the slope of the regression line. So in other words, what b means is for every unit increase in x, there is a corresponding predicted increase of b units in y. So every time this goes up by a certain amount, this is going to go up by a certain amount. Okay? So there's going to be some kind of corresponding. Or if b is negative, then, you know, that can maybe go down too. So some kind of correspondence between the two. Beta, okay, so this is called b. It's just straight up b. Beta is taking this, or taking b, and standardizing it in standard deviation units. So basically, beta is just taking this and converting it into standard deviation units. So I introduced both to you because some studies will just report this, other studies will report that, okay? So we're going to look at one that actually reports this, but sometimes you'll see this, okay? But what they're basically saying is that the b that we found for this variable exercise was, you know, was 1.25. So for every 1.25 hours of exercise that somebody has, weight goes up. Okay, let's just say this person's a weightlifter, so exercising makes them bigger. Okay, so that would be the b. Okay, and beta would turn that 1.25 into standard deviation units. So maybe it might be like 0.25 or 0.1. So they'll say for every 0.1 standard deviation unit that this goes up, that b goes up, y goes up, something like that. So you should know both, but they're basically one is unstandardized. It's just the units. This is standardized in standard deviation units. Okay. So that's to understand the variables individually. So what we just looked at was how each variable as an individual gets measured and what's important there. So remember, for individual variables in a regression, what you're interested in is B or beta, whichever one the study is trying to report. Now, when you're interested in the variables as a group, so right now, so last time we were just talking about, height, exercise, calories. We were just looking at them individually. So for multiple correlation coefficients, this is when you're interested, how do the variables as a group correlate with the dependent variable? So the multiple correlation coefficient is a capital R. So remember, the Pearson was a lowercase r. When you're dealing with multiple regression, the R gets capitalized because you're talking about several predictor variables. So this is the measure of correlation between the combined predictor variables, so all of them as a group, and the dependent variable, okay? So that's the multiple correlation coefficient. When we combine height, exercise, and calories together, how well do they predict weight? The multiple correlation coefficient of determination simply measures the effect size of the combined variables. So remember, this is just like R squared, but for multiple regression. That's pretty much it. And then some places will report adjusted R squared, and so it's the adjusted correlation coefficient of determination. And all it basically does is it just takes into account some of the error associated of having multiple predictor variables, just, random variation. So it's not going to be significantly different from this, but it might be like 0.1 or something less. It's just to be like a little bit more accurate, right? But don't worry if so is it like a huge difference? No, it's usually very minor. So that's why a lot of people don't report this, but some do. Okay, so it's just all about the journal and what's standard for that journal. Okay. Okay, so now let's look at an example of a study finding. So a multiple regression analysis was conducted to examine the predictors of extroversion. So we're trying to predict extroversion here, okay? So 4 predictors were simultaneously entered into the model: age, self-efficacy, motivation, and gender. So we can imagine that they're wondering, how do these 4 variables predict extroversion? So we might have a variable for age, then a variable for self-efficacy. Let's call it self-F. Like go F through self, right? Okay, anyways, motivation, okay, and gender, okay? And what we're trying to figure out is, how do these all work together to predict extroversion, okay? So 4 predictors were simultaneously entered into the model, and then together these predictors accounted for 11% of the variance of extroversion. So working as a team here, if we put them all together, they can account for 11% of the variance of extroversion, okay? So they can explain up to 11% of extroversion, or at least there's 11% correspondence between them as a whole and extroversion, reporting extroversion. So all of these variables, except for gender, were significant predictors of extroversion, with age having a beta weight of -21 and self-efficacy having a beta of -20. They were the strongest predictors and were negatively associated with extroversion. So as age goes down, extroversion goes up. As self-efficacy goes down, because it's negative, extroversion goes up. Now it sounds kind of weird, like really age goes down and people become more extroverted, and their self-efficacy goes down, they become more extroverted? I don't know, interesting. But they were the strongest predictors and were negatively associated with extroversion. Whereas motivation was positively associated with extroversion. So the more motivated you are, the more extroverted you are, okay? So there it's a positive, it goes in a positive direction, okay? So that's pretty much it. So usually when you look at multiple regression, different things will get reported, but you'll usually find something like this. You'll usually find something with a beta. You might see a t statistic too, just to show that the correlation or the coefficient that they got was beyond chance. So you might see t values reported, p values reported, but you already know what all those things are, so it's all good. So that's pretty much it for correlation and regression. So that's as deep we're going to go. If you're interested in statistics and find this all cool and fascinating, help yourself to a lot of statistics classes in the statistics department. And until then, that's all, folks.